Welcome to the Deep Dive. Today we're taking on a pretty substantial pile of information, a whole collection of ASE test prep books, actually.
Right. Quite the stack.
Exactly.
Yeah.
And our mission, like always, is to really boil it down, pull out those crucial insights you need. We want to give you a serious shortcut to being well-informed.
Whether you're, actively studying for the ASE certification.
Or you're a seasoned tech, an enthusiast, maybe just curious about how these amazing machines actually work.
And it's a worthwhile mission. ASE, the National Institute for Automotive Service Excellence, they've been setting the standard since, 72?
That long, wow.
Yeah, promoting high-quality service and repair. It's a nonprofit, and we're talking over 400,000 certified professionals.
Across like 40 different specialties, right?
More than 40, yeah. And that certification, it's not just, a badge. It really shows knowledge, experience, boosts your career, definitely, and customer confidence, too.
That's huge.
Absolutely. Now, the tests themselves, they're mostly multiple choice. You get your direct questions, most likely scenarios, those technician A says, technician B says types.
Yes, Phil.
And the acceptee questions, always tricky. But look, for this deep dive, we're not just going to, list facts from the book.
No, definitely not.
We want to build a narrative, explain the why and the how behind these core automotive concepts, and the time we spend on each topic, it'll be, roughly proportional to how much weight it carries in the actual tests.
Makes sense. So where should we kick things off? How about we dive right into maybe one of the most complex systems, transmissions and transaxles, that whole power transfer puzzle?
Sounds good. It's a system that really shows off some clever engineering.
Yeah.
Getting that power from the engine to the wheels efficiently, reliably, it's absolutely vital.
So where do we start? Diagnosis.
Yeah, let's start with diagnosis. Because with transmissions, it often feels a bit like detective work, honestly. Hashtag general transmission transaxle diagnosis, 6.1%. And surprisingly, maybe, the starting point for automatic transmission diagnosis is often the torque converter.
Okay, the fluid coupling between the engine and transducer.
Exactly. It connects them without a solid mechanical link, all done with fluid dynamics. It's got four main players inside: the impeller, the turbine, the stator, and the converter clutch.
So walk us through that. How do those four parts work together? How does the power actually flow?
Okay, so picture the impeller, sometimes called the pump. It's bolted to the engine's flywheel or flex plate, so it spins with the engine.
Got it. Engine spins, impeller spins.
Right, and as it spins, it slings automatic transmission fluid, ATF, outwards. Think of it like a fan blowing fluid.
Okay.
That moving fluid then hits the blades of the turbine. The turbine is connected to the transmission's input shaft. So the fluid hits the turbine, makes it spin, and that's what sends power into the transmission.
So that's the basic fluid coupling, like your two fans analogy. One blows, the other spins.
No, exactly. That's the core idea. But then comes the stator, and this is where it gets really clever.
Right. The stator isn't just sitting there, is it? It does something important.
It's the unsung hero, absolutely. It sits between the impeller and the turbine, and crucially, it's mounted on a one-way clutch, the stator overrunning clutch.
One-way clutch. So it can lock or spin freely.
Precisely. Its job is to redirect the fluid flow. When you're accelerating, the engine's spinning much faster than the transmission input shaft, right?
Yeah. Big speed difference.
So the fluid comes off the turbine heading back toward the impeller. The stator catches that returning fluid and redirects it, hitting the back of the impeller blades in a way that actually multiplies the engine's torque.
So it's like a fluid-based gear reduction almost. Gives you that extra push off the line.
You got it. It's a torque multiplier. That's key for acceleration.
Yeah.
But once you get up to cruising speed, the impeller and turbine speeds get closer.
Less need for multiplication.
Right. And the fluid flow changes direction slightly. That unlocks the stator's one-way clutch, allowing it to spin freely with the impeller and turbine. This reduces drag, boosts efficiency, saves fuel.
So a faulty stator could mean sluggish acceleration and bad mileage.
Definitely. And the fourth piece, the converter clutch, usually a friction clutch inside the converter, locks the impeller and turbine together mechanically at cruising speeds.
Eliminating slip altogether for maximum efficiency.
Exactly. No fluid slip, direct drive, better fuel economy. So the torque converter isn't just a simple coupling, it's adaptive. It multiplies torque when needed, allows efficient cruising, and locks up for direct drive. It's a smart power breaker.
That's a great explanation. Okay, so we know how it should work.
Yeah.
But when things go wrong, what are the go-to resources?
Yeah.
Service info, diagnostic tools.
Oh, absolutely essential. Troubleshooting charts are invaluable. They link symptoms like, say, harsh shifts or slipping to potential causes and conditions, saves a ton of guesswork.
And shift schematics.
Those are your roadmaps for the hydraulic system. They show which clutches and bands are applied in each gear. Super helpful for figuring out, say, why third gear isn't engaging.
Okay. And pressure charts.
Pressure specification charts are key. You need to verify the actual fluid pressures during operation match what the manufacturer specifies. Low pressure in a particular circuit points directly to leaks or pump issues.
Right. Makes sense. Now, diagnostic trouble codes, DTCs. That's the computer side. What are we looking at there?
DTCs are fundamental. You've got your hard codes, meaning the problem is happening right now,
Always present.
and soft codes, which are intermittent. They might be stored in history, but the fault isn't active at this exact moment. Maybe it only happens when it's cold or hot.
Tricky ones.
They can be. And you also have generic SAE codes, like a P0700, which just says transmission control system malfunction.
Not very specific.
No, but then you have manufacturer-specific codes that give you much more detail, and that's where scan tools are indispensable.
More than just reading codes, right?
Oh, yeah. Modern scan tools let you see snapshot data or freeze-frame data. That's the vehicle's vital signs, sensor readings, temperatures, speeds captured at the exact moment the code was set.
Like a black box recording.
Kind of, yeah. It gives you context, what was happening when the fault occurred. Plus, you get live data streams and bidirectional controls.
Meaning you can command things to happen.
Exactly. You can tell the computer to activate a specific shift solenoid or turn on the converter clutch and see if it responds correctly. It's huge for confirming a diagnosis without tearing things apart unnecessarily.
So you've got the digital side covered with scan tools and codes. What about the hands-on diagnosis, the feel of it?
Still crucial. A road test is non-negotiable. You need to experience the customer's complaint firsthand, feel the shifts, listen for noises, check engagement under different loads and speeds.
Get a bucket line.
Precisely. And your multimeter is your best friend for electrical checks. Voltage drop tests are especially powerful.
We keep hearing about those. Why so important?
Yes, because high resistance in a circuit causes voltage to drop. The power doesn't get where it needs to go. A voltage drop test pinpoints that resistance, whether it's a bad connection, corroded wire, or failing component. It can mimic other failures, so it's key to rule it out.
And common problems technicians look for.
Slipping is a big one, often pointing to warm clutches or low fluid pressure. Harsh shifts could be solenoids, valve body issues, or even high pressure. Delayed engagement, say going into drive or reverse, might be low fluid, filter issues, or internal seals. It's about combining the codes, the data, the road test feel, and the electrical checks. #BB, in-vehicle transmission transaxle repair, 3.2%.
Okay, diagnosis done. Now, sometimes you can fix things without pulling the whole transmission out. What about in-vehicle repairs, like drive axle bushings and seals?
Right. Replacing seals, like axle seals or the output shaft seal, is pretty common in vehicle work. Precision is key there. You need the right tools, often specific seal drivers, to install them straight and without damage.
Can't just hammer them in.
Definitely not. And lubrication is critical, lubing the seal lip. And the shaft ensures it seals properly and doesn't get damaged during installation. While you're there, you always check for excessive looseness in related parts, like bushings. No point putting a new seal in if the shaft it seals is wobbling around.
Makes sense. What about the transmission extension housing? The tail housing?
That can sometimes be removed in the vehicle, too, depending on the design. You'd need to support the transmission securely, of course, then disconnect the drive shaft, maybe speedometer cables or sensors.
Unbolt the housing itself.
Exactly. And when putting it back, again, lubrication is important. Lubing the U-joints where the drive shaft connects, the differential pinion flange, ensures everything goes together smoothly and operates without binding.
And for front-wheel drive cars, replacing a transaxle differential seal. Any special considerations there?
Yeah, FWD adds complexity because you're dealing with the CV joints and stub shafts coming out of the transaxle.
The drive axles.
Right. You have to carefully remove the drive axle from the transaxle to get access to the seal. It means being careful not to damage the CV boots or the joints themselves during removal and installation. A torn boot leads to dirt getting in, and a failed CV joint soon after.
Gotcha. And even if you're not doing a full rebuild, sometimes you might need to do some minor disassembly in the car. What kind of parts are we talking about?
Sure, sometimes you might need to access the valve body, which is like the hydraulic brain of the transmission, or maybe replace accumulators, which cushion the shifts.
Smooth things out.
Yeah. Or even access the fluid pump components in some cases. A critical check, especially if the torque converter was out, is converter end play, making sure there's the right amount of clearance. And as an example, you might remove a servo cover, piston, and spring. Servos apply the bands that grip drums to help engage gears. Replacing servo seals or springs can sometimes fix shift problems without a full teardown. Hashtag CBay. Transmission transaxle maintenance and adjustment, 2.9%.
Moving from fixing problems to preventing them. Maintenance and adjustment. Fluid leaks seem like a really common transmission issue. Where do they usually come from?
They are very common, and often they start small but can lead to big trouble if the fluid gets too low. Common leak spots include the speedometer, cable housing O-ring, the extension housing gasket or seal, and the rear output shaft seal. Pan gaskets are another frequent culprit.
So how do you pinpoint a leak? Sometimes the whole underside is oily.
Right. The first step is always to thoroughly clean the suspected area. Get all the old grime off. Then you might run the engine, maybe drive it briefly, and look for fresh fluid. Sometimes applying a light powder, like an aerosol foot powder, can help. The leaking fluid makes a dark track in the white powder, making it easier to trace it back to the source.
Clever trick. What about external shift linkage? What needs checking there?
You need to inspect the linkage for any signs of wear or damage. Are any rods bent? Are the bushings worn out, causing looseness? Are connections tight? Worn linkage can cause sloppy shifting, difficulty finding gears, or even prevent park from fully engaging. And adjustment.
Adjustment procedures vary, but often there's an alignment mark or a specific gauge slot you use to ensure the linkage puts the transmission lever in the exact position corresponding to the gear selector inside the car. Precision matters here.
Okay. And switches and sensors on the transmission, how do they fit into maintenance beyond just setting codes?
Well, they're critical inputs, the reverse light switch, for instance. It turns on your backup lights, sure, but it also tells the transmission control module, TCM, and sometimes other modules that you're in reverse. That affects things like backup cameras or parking sensors.
Right, it's integrated.
And the vehicle speed sensor, the VSS. It doesn't just drive the speedometer. The TCM uses that VSS signal for shift timing, convert clutch lockup. Cruise control relies on it too.
So ensuring these switches and sensors are working correctly and adjusted properly is part of keeping the whole system happy. Absolutely. It really raises the question, how much does that precise adjustment impact the long-term health and performance? Even a slightly misadjusted linkage or an erratic VSS signal can, over time, lead to increased wear, poor shift quality, and reduced fuel economy. Small things can add up. Hashtag D manual drivetrain and axles, 1.2%.
Okay, let's switch gears literally to manual drivetrains. Clutch problems. What are the typical symptoms and checks?
With clutches, you're often listening for the driver's complaint first. Is it making noise, slipping under load, chattering when engaging? Is the pedal feel wrong, too hard, too soft, spongy?
So start with the symptoms.
Always. Then inspection involves checking the clutch disc for where how much lining is left, checking the pressure plate for scoring, heat spots, or broken springs. The release bearing or throw-out bearing needs checking for noise or roughness when spun. And don't forget the pilot bearing or bushing in the crankshaft. If that's worn, it can cause noise and input shaft issues.
What about the hydraulic side of a clutch system?
Right. Many modern clutches are hydraulic. So you need to inspect the master cylinder, the slave cylinder, and the lines connecting them. Check the fluid level and condition. Look for leaks. Air in the hydraulic system is a common cause of a soft or ineffective pedal.
Got it. And for manual transmissions or transaxles themselves, what goes wrong there?
Common complaints are noise whining, grinding, difficult shifting, gears clashing during shifts, or fluid leaks.
And diagnosis.
Externally, you check the shift linkages for wear or adjustment issues, inspect the transmission mounts, and look for leaks from seals or gaskets. Internally, if you suspect problems, you'd be looking for worn gears, damaged bearings, or very commonly worn synchronizer rings.
The synchros are what make shifting smooth, right?
Exactly. They match the speed of the gear you're shifting into with the speed of the input shaft. Worn synchros are a prime cause of gear clash or grinding.
Okay. And finally in this section, drive axles, drive shafts, U-joints, CV joints. What's the focus there?
Inspection, inspection, inspection. Look for wear and damage. On a typical rear-wheel drive setup, you inspect the drive shaft itself for balance weights or damage and check the universal joints or U-joints for any stiffness or play. They allow the drive shaft angle to change as the axle moves.
And front-wheel drive.
You're looking at the drive axles, which have constant velocity, or CV joints. The big thing here is inspecting the rubber boots covering the CV joints. If a boot is torn or cracked, grease escapes, dirt gets in, and the joint wears out very quickly, causing clicking noises, especially during turns. For rear axles, you're checking the differential for leaks or noise, and the axle shafts themselves. #E automatic transmission transaxle, 1.0%.
So we've covered a lot on transmissions generally. How does this specific smaller section on automatics tie everything together? What's the takeaway?
It really just reinforces the points we made earlier, especially in the general diagnosis part. Automatics are incredibly reliant on that precise stance between hydraulic pressure and electronic controls.
The complexities.
Right. Their smooth, efficient operation hinges on it. So this section basically loops back and emphasizes that fundamental diagnosis, checking fluid level, checking fluid condition, basic operational checks like engagement feel is always the starting point. Any issues there ripple through the whole complex system. You have to get the basics right before diving deeper.
Okay, we've handled how power gets to the wheels. Now let's go to the source, the engine itself. This is a huge area for ART. It looks like almost 40% of the content combined across the different tests. So yeah, let's really get into the heartbeat of the vehicle.
Absolutely. The engine is the core, no question. Understanding how to diagnose it, how its performance systems work, the controls, it's fundamental. We should probably start with general engine diagnosis. That's often the first step, the foundation for everything else. #TAG, general engine diagnosis, 11%. And those initial steps are so critical. It always starts with verifying the customer's complaint. What exactly are they experiencing? When does it happen?
Get the full story.
Get the full story. Then, a road test is vital to try and duplicate the condition, feel how the engine performs under different loads, and a thorough visual inspection, you'd be amazed what you can find. Leaks, loose wires, disconnected vacuum hoses, damaged components.
The simple stuff first.
Always. And don't forget technical service bulletins, TSBs, and recalls. Manufacturers often put out information on known issues and fixes. Checking for those can save hours of diagnostic time if it's a common problem. Like that one time a customer complained about a noise. Quick look underneath, loose exhaust heat shield, 5-minute fix.
Huh. Beats tearing the engine apart. Okay, before even diving into the engine, what about the systems that get it going? Battery and starting.
Absolutely fundamental. If the engine won't crank slowly, or cranks but won't start, the battery is suspect number one. Check its voltage. A fully charged battery should be around 12.6 volts open circuit.
Not 12 volts flat.
No, 12.6 or slightly higher. Then, for flooded batteries, you check specific gravity with a hydrometer. And a load test is crucial. It measures the cold cranking amps, or CCA, the battery can actually deliver.
Tells you its real strength.
Exactly. Then the starter itself, a starter current draw test tells you how much amperage it's pulling. Too high means a potential starter issue or engine problem. Too low might be high resistance in the circuit.
Like a voltage drop.
Precisely. Voltage drop tests on the main battery cables and the starter control circuit are key to finding that hidden resistance. You can have a good battery and a good starter, but if the power can't get there efficiently, it won't work right.
So you can't diagnose the engine if it won't even start properly.
You got it. Fix the foundation first.
Okay, engine noises, they can be really hard to pinpoint. How do technicians approach that?
It takes practice and a good ear, sometimes helped by a stethoscope. We generally try to categorize the noise. Is it coming from the bottom end? That might be crankshaft-related main bearings, rod bearings, wrist pins, maybe excessive crankshaft in play, usually deeper knocking sounds.
Okay, what about higher up?
Valve-train noises are common. Ticking or clattering sounds could be worn rocker arms, lifters, tappets, push rods, camshaft lobes, even timing gears or a timing chain.
Lots of possibilities there.
Yeah, and then there are other noises, a whining oil pump, spark knock, or pinging from detonation, a hissing vacuum leak, a puffing exhaust leak. Using a mechanic's stethoscope helps you narrow down the location. Listen at the valve cover, the block, the oil pan.
Like a doctor listening to a patient.
Pretty much.
Yeah.
Pinpointing the source is half the battle.
Now here's a tool that seems kind of old school, but incredibly useful. The engine vacuum gauge. What can that tell you?
Ah, the vacuum gauge. It's fantastic. You connect it to a source of intake manifold vacuum, and it gives you a real-time picture of the engine's breathing and internal sealing.
What's a normal reading?
On a healthy, warm engine at idle, at sea level, you're looking for a steady reading between 17 and 22 inches of mercury in HD.
Steady is key.
Steady is key for a healthy engine, but you have to adjust for altitude. For every 1,000 feet above sea level, you subtract about 1 inch of mercury from that expected range.
Okay, so altitude matters. What about when the needle isn't steady?
Ugh.
What do the fluctuations mean?
That's where the real diagnostic power comes in. For example, an intermittent drop or flicker at idle often points to a sticking valve. A low but steady reading could be several things. Retarded ignition timing, uniformly low compression, a significant vacuum leak, like a leaking intake manifold gasket. A low but steady reading could be several things. A high but steady reading can actually indicate a restricted exhaust, like a clogged catalytic converter.
Interesting. High vacuum means blocked exhaust.
Yeah, seems counterintuitive, but the engine can't exhale properly. If the needle drops sharply and regularly with each engine revolution, that's a classic sign of a burnt valve or poor valve seating. A needle that vibrates rapidly at idle but smooths out as RPM increases often indicates worn valve guides.
Wow, that's a lot of information from one simple gauge.
It really is. It gives you a quick overall health check of the engine's mechanical condition, valve sealing, ring sealing, breathing efficiency. Often the first test I reach for if I suspect internal issues.
Okay, so vacuum gives a general picture. How do you zero in on specific cylinders if you suspect one isn't pulling its weight?
That's where a cylinder power balance test comes in handy. The idea is to disable one cylinder at a time, either by grounding the spark plug wire or, on modern cars, using a scan tool to disable the fuel injector and watch the RPM drop.
And you're looking for consistency.
Exactly. Each cylinder should contribute roughly equally. If disabling one cylinder causes a much smaller RPM drop than the others, that cylinder is weak. It's not contributing its fair share.
Makes sense. And then compression testing.
The classic compression test. You remove all the spark plugs, disable fuel and ignition, and crank the engine with a pressure gauge screwed into each spark plug hole. First, a dry test. Record the peak pressure for each cylinder. Again, you're looking for consistency, generally within 10–15% of each other.
What if one is low?
If one or more are low, you do a wet test. Squirt a small amount of engine oil into the low cylinder and repeat the test.
Why the oil?
The oil temporarily helps seal worn piston rings. So if the compression reading jumps up significantly on the wet test, it strongly suggests the problem is worn rings. If it stays low, the problem is more likely in the valvetrain burnt valve, bent valve, poor sealing, or maybe a head gasket issue.
So dry test, then wet test to differentiate rings versus valves. What are common causes of low compression overall?
Worn piston rings, burnt or sticking valves, a blown head gasket between cylinders or to a water jacket, maybe even a hole in a piston, though that's less common.
Okay, and one more test in this area, cylinder leakage. How does that differ from compression?
A cylinder leakage test or leak down test is more precise. Instead of measuring peak pressure during cranking, you bring the piston to top dead center, TDC, on its compression stroke so both valves are closed.
Piston at the top, ready to fire.
Right. Then you introduce compressed air into the cylinder through the spark plug hole using a special gauge that measures the percentage of air leaking out. A healthy cylinder might have maybe 5–10% leakage. Over 20% usually indicates a problem.
And the key is where the air is leaking to, right?
Yeah, actually, that's the beauty of it. While the cylinder is pressurized, you listen. Air hissing out the tailpipe, leaking exhaust valve, hissing from the throttle body or air intake, leaking intake valve, hissing from the oil filler cap or dipstick tube, air getting past the piston rings into the crankcase, bubbles appearing in the radiator coolant, leaking head gasket or cracked cylinder head block.
So it pinpoints the exact location of the leak, much more specific than just knowing compression is low.
Precisely. It really helps narrow down the diagnosis before you start taking things apart. ####B, computerized engine controls diagnosis and repair, 3.2%.
Okay, moving from the mechanicals to the electronics. Computerized engine controls. Modern engines are covered in sensors feeding data to the computer, the ECM or PCM. What's the biggest challenge when dealing with all these signals? Can they mislead you?
Oh, absolutely they can. That's probably the biggest challenge, interpreting the data correctly. A fault code for one sensor doesn't always mean that specific sensor has failed.
It could be reacting to something else.
Exactly. It could be reporting accurately on an abnormal condition caused by something else entirely. A classic example is a mass airflow, MAF, sensor code. The MAF sensor might be working perfectly fine, but if there's a vacuum leak after the sensor...
Unmetered air getting in.
Right. The engine gets more air than the MAF sensor measured. The oxygen sensors detect a lean condition. The computer tries to compensate. And it might flag the MAF sensor reading as implausible, even though the leak is the real root cause. So you have to look at the whole picture, correlate different sensor readings. These sensors are the engine's eyes and ears, translating physical conditions, temperature, pressure, airflow, position into electrical signals the computer understands.
Okay, let's run through some of the key sensors. The intake air temperature, or IAT sensor.
The IAT, usually a simple thermistor. Its resistance changes predictably with the temperature of the air entering the engine. Colder air is denser, requires more fuel. Hotter air, less dense, less fuel. The PCM uses that IAT signal as part of its calculation for fuel mixture.
Manifold absolute pressure, MAP sensor.
The MAP sensor measures the pressure, or vacuum, inside the intake manifold. It's a primary indicator of engine load. Heavy load, like climbing a hill, means low vacuum, high manifold pressure. Light load, like cruising, means high vacuum, low pressure. The PCM uses this MAP signal to adjust fuel delivery and ignition timing based on load.
And the mass airflow, MAF sensor. You mentioned that one.
Right. The MAF sensor directly measures the mass of air entering the engine, usually using a heated wire or film. Air flowing past cools the element, changing its resistance. The computer knows how much current is needed to keep it at a constant temperature, and that's proportional to the air mass. It's a very precise measurement, critical for accurate fuel control.
Throttle position sensor, TPS. That seems straightforward, tells the computer how far the driver's foot is down.
Pretty much, yeah. It's usually a potentiometer connected to the throttle shaft. As the throttle opens and closes, the sensor's voltage output changes. The PCM uses this signal for, well, everything. Fuel injection, ignition timing, transmission shift points, idle speed control. Very important input.
Vehicle speed sensor, VSS. We touched on this with transmissions.
Yep. Often a magnetic pickup sensor on the transmission output shaft or sometimes at the wheels. It generates a signal, usually AC voltage, whose frequency increases with speed. Used for the speedometer, cruise control, ABS, transmission shifting, lots of things.
Okay, two critical ones. Crankshaft position, CKP, and camshaft position, CMP sensors.
Absolutely critical. These tell the PCM exactly where the crankshaft and camshaft are in their rotation. They work together to provide engine speed information and precise piston position. This is essential for synchronizing fuel injection and ignition timing.
What happens if one fails?
A failing CKP sensor will often result in a no-start condition. The PCM simply doesn't know when to fire the spark plugs or injectors. A CMP sensor failure might allow the engine to run, but could cause issues with sequential fuel injection or variable valve timing, leading to poor performance or rough running. They can use different technologies. Hall effect sensors create a digital square wave signal, while magnetic reluctance sensors generate an analog AC sine wave.
And the knock sensor, KS.
The knock sensor listens for abnormal combustion or engine knock, often caused by low-octane fuel or incorrect timing. It's usually a piezoelectric sensor. It generates a voltage when it detects the specific vibration frequency of knocking. When the PCM sees that signal, it immediately retards ignition timing slightly to stop the knock and protect the engine from damage.
So if you've diagnosed everything else, and you suspect the actual computer, the PCM or ECM, is faulty, replacing it isn't just plug and play, is it?
Rarely. Replacing the PCM is usually a last resort, but if it is necessary, it almost always requires programming or initialization using a factory-specific stand tool. The new PCM needs to be configured for the specific vehicle VIN number, options, and mobilizer system integration. You can't just swap one from another car. #TAG-C. Fuel, air induction, and exhaust systems diagnosis and repair, 11.5%.
All right, let's talk about getting fuel and air into the engine and exhaust out. These systems are obviously crucial for performance, economy, and increasingly emissions. Let's start with the fuel system.
Okay, fuel system basics. Inspection is key, looking for leaks in the lines, hoses, connections. O-rings can dry out and crack. Check the fuel filter, check the pump operation. Fuel pressure and volume tests are fundamental diagnostic steps.
How do you do those?
For pressure, you connect a fuel pressure gauge to the fuel rail or test port. Check pressure with the key on, engine off, then engine running, and maybe under load. Compare it to specs. Low pressure could be a weak pump, clogged filter, or bad regulator. For volume, you might disconnect the fuel line and run the pump for a specific time, collecting the fuel in a graduated cylinder to measure the flow rate. Again, compare to specs.
And ethanol content, that's becoming more of a factor, right?
It is, especially with flex fuel vehicles. High ethanol concentrations can sometimes affect certain fuel system components not designed for it, potentially causing material degradation or issues with sensors that measure ethanol content. There are specific tools to test the ethanol percentage in the fuel if you suspect related problems. Bottom line, the engine needs the right amount of fuel at the right pressure consistently.
Makes sense. Moving to air induction and exhaust. The air filter seems simple, but
Critical. A dirty, clogged air filter restricts airflow, plain and simple. That hurts performance and fuel economy. Visual inspection is usually enough. Just replace it if it's dirty.
Okay, what about the PCV system?
Yeah.
Positive crankcase ventilation?
Ah, the PCV system. Often overlooked, but really important. Its job is to remove combustion blow-by gases from the engine's crankcase.
Gases that sneak past the piston rings.
Exactly. These gases contain moisture and unburnt fuel that can contaminate the oil and build up pressure inside the crankcase, potentially blowing out seals. The PCV system uses engine vacuum to draw these gases out of the crankcase and write them back into the intake manifold to be burned.
So it keeps the oil cleaner and prevents pressure buildup. How do you check it?
It usually consists of a PCV valve and some hoses. You check for vacuum at the valve itself. Often you can pull the valve out and shake it. A good mechanical valve should rattle. Inspect the hoses for blockage, cracks, or collapse. A stuck closed PCV valve can cause pressure buildup and oil leaks. A stuck open one can act like a vacuum leak, causing lean running or rough idle.
Okay, now for engines that need a little extra help breathing, superchargers and turbochargers. Forced induction.
Right. Both do the same basic job. Compress the intake air, forcing more air molecules into the cylinders. More air means you can burn more fuel, which means more power.
What's the difference between them?
A turbocharger uses the energy of the engine's exhaust gases. Exhaust spins a turbine wheel, which is connected by a shaft to a compressor wheel on the intake side. That compressor wheel sucks in air and forces it into the engine. A supercharger is mechanically driven, usually by a belt connected to the engine's crankshaft. It uses that mechanical energy to spin the compressor.
So turbo uses waste energy, supercharger uses engine power directly.
Essentially, yes. Key components are the turbine, on a turbo, the compressor, and critically for turbos, the wastegate.
Ah, the wastegate. Why is that so crucial?
The wastegate is a bypass valve. It controls how much exhaust gas actually goes through the turbine. Without it, as engine speed and load increase, the turbo would just keep spinning faster and faster, creating potentially damaging levels of boost pressure. The wastegate opens at a preset pressure limit, diverting some exhaust gas around the turbine directly into the exhaust pipe to regulate the maximum boost pressure.
So it protects the engine from overboosting.
Exactly. It's vital for performance and longevity. Diagnosing forced induction systems involves checking for air leaks in the intake plumbing, boost leaks, verifying the actual boost pressure matches the commanded pressure using a scan tool or gauge, and ensuring proper lubrication, especially for turbos which spin incredibly fast and get very hot. And of course, the exhaust system itself needs to be in good shape. Any restrictions downstream can increase back pressure and hurt turbo performance.
Which brings us to emissions controls. You mentioned these aren't just about passing tests, they're integrated engineering systems. Let's start with EGR.
EGR, exhaust gas recirculation. Its main job is to reduce the formation of nitrogen oxides, or NITACs, which are created under high combustion temperatures and pressures.
How does it do that?
It introduces a small, precisely controlled amount of inert exhaust gas back into the intake manifold, mixing it with the incoming air-fuel charge. This exhaust gas doesn't burn, so it effectively dilutes the mixture, which lowers the peak combustion temperature. Lower temperature means less NOx formation.
The lever. What are the components?
Usually an EGR valve, which can be vacuum-operated or electronically controlled, maybe a solenoid to control vacuum or the valve directly, and PCM control. Diagnosis involves checking if the valve holds vacuum, if applicable, using a scan tool to monitor the commanded versus actual EGR position on electronic valves, and checking for carbon buildup, which is a very common reason for EGR valves sticking open or closed.
Okay, what about secondary air injection, AIR system?
The AIR system helps reduce carbon monoxide, CO, and hydrocarbon, HC emissions, primarily during cold starts before the catalytic converter is fully warmed up and effective.
Ow.
It pumps fresh air directly into the exhaust manifold or sometimes into the catalytic converter itself. This extra oxygen helps burn off any unburnt fuel, HC, and convert CO into less harmful CO2 in the exhaust stream. Components include an air pump, electric or belt-driven, diverter valves to direct the airflow, and check valves to prevent exhaust from flowing back into the pump. Diagnosis involves checking if the pump runs, if the valves are directing air correctly, and if the check valves are holding.
In the final stage. The catalytic converter.
The catalytic converter is like a chemical processing plant for exhaust gas. It contains precious metals like platinum, palladium, and rhodium that act as catalysts. They trigger chemical reactions to convert harmful CO, HC, and NOx into much less harmful water, H2O, carbon dioxide, CO2, and nitrogen, N2.
How do you know if it's working or if it's locked?
Diagnosis can involve several things. A back pressure test checks for restrictions. A clogged converter will significantly impede exhaust flow. An exhaust gas analyzer, measuring gases before and after the converter, can determine its conversion efficiency. And a visual inspection can reveal physical damage or signs of overheating, like a glowing red shell, which usually means it's plugged up, often due to an engine problem upstream causing excessive unburnt fuel to enter it. Connecting this all together, emissions controls show a huge engineering effort to make engines powerful and clean, balancing performance with environmental needs. Hashtag D ignition system diagnosis and repair, 2.0%.
Okay, so let's talk ignition, the spark that makes it all happen.
Yeah.
What are the main system types we see?
We've definitely seen an evolution. Older systems used a distributor or DI with a single coil, a cap, rotor, and plug wires. Then came electronic ignition or EI, which often eliminated the distributor for spark timing but might still use a coil pack and wires. And now coil on plug or COP is very common, where each spark plug gets its own dedicated ignition coil right on top of it.
Eliminates the wires.
Exactly, but the fundamental principle is the same across all types. Take low voltage, 12V from the battery in the primary circuit, run it through the coil's primary winding, then interrupt that current flow very quickly. This rapid collapse of the magnetic field induces a very high voltage, tens of thousands of volts in the coil's secondary winding.
Step-up transformer action.
You got it. That high voltage then travels through a wire or directly in COP systems to the spark plug and jumps the gap, creating the spark that ignites the air-fuel mixture.
So inspection is pretty key for these high-voltage components.
Absolutely critical. Spark plugs need regular inspection. Look at the electrode condition. Is it worn, fouled, damaged? Check the gap with a feeler gauge. Is it correct for that engine? On systems with wires, inspect the wires for cracks, burns, chafing. Test their resistance with an ohmmeter. High resistance means less spark energy gets to the plug. For DI systems, check the distributor cap and rotor for cracks, carbon, tracking little black lines showing where spark is leaking, or corrosion on the terminals.
And when things aren't working right, no start, misfires. How do you diagnose?
A no start or hard start related to ignition could be low voltage, getting to the primary side of the coil, maybe an open circuit in the primary wiring, a faulty ignition switch, a bad crank sensor signal, so the computer doesn't know when to fire, or a failed ignition module or coil.
And misfires.
Engine misfires can definitely be ignition-related. A bad spark plug, a high-resistance wire, a cracked distributor cap, a weak coil, or a faulty ignition module can all cause intermittent or constant misfires on one or more cylinders.
How do you test individual components?
You check the ignition switch for proper voltage output in the run and start positions. Ignition coils can be tested for primary and secondary winding resistance using an ohmmeter or compare the readings to specs. Pickup coils and distributors or crank cam sensors can be tested for resistance and also for AC voltage output while cranking if they're magnetic reluctance type. Hall effect sensors need to be checked for proper power, ground, and signal output, usually a square wave, using a multimeter or oscilloscope. And don't forget the secondary components, high resistance in spark plug wires or boots is a common, often overlooked cause of misfires. Hashtag E, cylinder head, and valve train diagnosis and repair, 3.6%.
All right, let's dive deeper into the engine's top end, the cylinder head and valve train. This is the engine's respiratory system, controlling airflow in and exhaust out.
Precisely. It's a precision mechanism. You've got the intake and exhaust valves, valve springs to close them, retainers and keepers to hold the springs on, rocker arms to transfer motion, push rods in some engines, lifters or tappets, and the camshaft itself, which orchestrates the whole dance with its lobes.
So lots of moving parts under stress. What kind of wear and damage are you looking for during inspection?
You need to be meticulous. Measure the valve stems for wear using a micrometer. Check for signs of damage like nicks, bent stems, or excessive wear in the keeper grooves. Inspect the valve faces and seats for pitting or burning, which indicates poor sealing.
What about the valve guides, the channels the stems slide in?
Critical check. Look for signs of inadequate lubrication or excessive wear. Worn guides allow the valve to wobble, preventing a good seal and often leading to high oil consumption as oil gets sucked down the guide. Cracked guides are also possible.
And the camshaft and lifters.
Inspect the camshaft lobes carefully. Look for pitting, scoring, or uneven wear. A wiped lobe, where the hardened surface has worn away, will drastically affect valve lift and duration. Measure the bearing journals for wear. Lifters, whether they're flat tappet or roller type, need inspection on their contact face. Any pitting, scoring, or concavity on flat tappets means replacement. For example, you'd use a micrometer to measure valve stem diameter at several points and compare to the manufacturer's wear limit. That tells you definitively if it's reusable.
And if repairs are needed, what's typically done?
It depends on the findings. Valve guides might be replaced, which can involve pressing out the old ones and pressing in new ones, sometimes requiring reaming to size. Or sometimes they can be repaired by knurling or installing thin wall liners. Valve seats often need reconditioning or replacement to restore a perfect sealing surface. Camshaft bearings are replaced if worn, and lifters are typically replaced if any wear is found on their face or roller. The key insight is that everything has to be within tight tolerances for the valvetrain to work correctly and quietly, ensuring proper engine breathing and performance. Hashtag tag ESHM engine block diagnosis and repair, 3.6%.
Let's move down to the foundation. The engine block, the lower end, the real heavy metal. What are the key players here?
You've got the cylinder block itself, which contains the cylinders. Inside those, you have the pistons connected to the connecting rods, which are in turn connected to the crankshaft. The crankshaft rides in the main bearings, supported by the block. The connecting rods attach to the crankshaft via the connecting rod bearings. It's the core rotating and reciprocating assembly.
And inspection here is all about precision measurement.
Absolutely. You measure crankshaft end play, the amount it can move fore and aft. Check crankshaft run out any bending. Measure the main and connecting rod bearing journals for wear, taper, and out of roundness using micrometers. Inspect the pistons for scuffing, cracks, or damage. Measure the piston ring grooves for wear. If they're too wide, the rings won't seal properly.
And the rings and cylinders themselves.
Measure the piston ring end gap, the gap when the ring is installed in the cylinder, and side clearance, the up and down clearance of the piston groove. Both affect sealing. Inspect the cylinder bores for wear, scoring, taper, wider at the top than the bottom, and out of roundness using a dial bore gauge. All these dimensions are critical for proper compression and oil control. For instance, excessive crankshaft journal wear means the bearing clearance will be too large, leading to low oil pressure and a potential bearing failure.
So when assembling this lower end, what are the really critical steps?
Proper piston and connecting rod assembly is crucial. That includes installing the piston rings in the correct order and orientation: top ring, second ring. Oil control rings often have specific up markings or chamfers. Correct installation of the main and connecting rod bearings is paramount. Ensuring the right oil clearance, often checked with plastigauge or dial bore gauge, is vital. Too tight, and the bearing seizes. Too loose, and oil pressure drops, and the bearing pounds out. And of course, using assembly lube generously on bearings and journals during assembly is non-negotiable to prevent dry start damage. Hashtag tag G lubrication and cooling systems diagnosis and repair, 3.5%.
Finally, for the engine itself, let's talk about the life support systems.
Yeah.
Lubrication and cooling. Absolutely essential.
Couldn't agree more. The lubrication system does so much more than just reduce friction. Yes, that's primary, but it also carries heat away from critical parts like pistons and bearings. It helps clean the engine by carrying contaminants to the filter, and it helps seal the piston rings against the cylinder walls.
What are the core components?
You have the oil pump, usually driven by the crankshaft or camshaft, which creates the pressure. The oil filter, obviously, to trap dirt and debris. The oil pan, which acts as the reservoir. And the network of drilled passages in the block and head. The oil galleries that deliver oil where it's needed.
And diagnosis. What usually goes wrong?
Oil leaks are very common, from gaskets like the oil pan or valve cover, or seals like the crankshaft seals. Low oil pressure is a serious concern. Could be a worn pump, worn engine bearings increasing clearance, a stuck pressure relief valve, or simply low oil level. High oil consumption is another issue, often related to worn valve guides or piston rings. And sometimes specific components are known weak points, like certain factory oil filter housing designs that are prone to cracking or leaking. The Pentastar V6 filter housing is a known example where aftermarket solutions often provide a more durable design.
Okay, and the cooling system. Its job seems simple.
Yeah.
Keep the engine from overheating.
Simple goal, complex system to achieve it reliably. Its main job is maintaining the optimal engine operating temperature. Too cold, and efficiency suffers, emissions increase. Too hot, and major damage occurs quickly.
Components.
You've got the radiator to dissipate heat to the air, the water pump to circulate the coolant, the thermostat to regulate the coolant temperature by controlling flow to the radiator, hoses to connect everything, and the coolant itself, which is usually a mix of antifreeze and water.
And common problems.
Leaks are number one from hoses, the radiator, water pump seals, heater core. Overheating is the other big one. Causes can include a clogged radiator, internally or externally with debris, a thermostat stuck closed, a weak or failing water pump, low coolant level, or even a faulty radiator cap that isn't holding pressure. It really highlights how these seemingly basic systems, lube and cooling, are utterly critical. They're the unsung heroes preventing catastrophic engine failure every time you drive.
Okay, let's shift focus now to what really makes a modern car tick. The electrical system. Yeah, it's like the vehicle's central nervous system, isn't it? Everything seems to run through it.
It absolutely is. And it's an area that has just exploded in complexity over the last couple of decades. Understanding how electricity flows, how circuits work, how components interact. It's fundamental to diagnosing almost anything on a car today. Hashtag tag A, tiny c. General Electrical Electronic System Diagnosis, 5.9%. Before diving into specific systems, it's worth quickly revisiting the basics. Voltage, think of it as electrical pressure measured in volts. Current, the flow of electrons, measured in amps. Resistance, the opposition to that flow, measured in ohms.
Volts, amps, ohms, the big three.
Right. And they're all related by Ohm's law. Understanding the difference between series circuits, where current has only one path, and parallel circuits, where it has multiple paths, is also crucial for troubleshooting how voltage drops and current divides.
You mentioned voltage drop again. We talked about it for starters, but it's a key electrical test overall, isn't it? Why is it so powerful?
It's powerful because it directly measures the loss in a circuit due to resistance. Ideally, electricity should flow from the source to the load and back with minimal loss. A voltage drop test checks specific sections of a circuit, like across a switch, a connection, or a length of wire while the circuit is operating.
Under load.
Yes, that's key. It tells you exactly how more voltage isn't making it to the component. Generally, you want to see very low drops, often less than 0.1 V across a connection or switch, maybe 0.2 V across a short wire, perhaps less than 0.5 V for a whole circuit section. High voltage drop means high resistance, which means the component won't get the power it needs to work correctly. It's a fantastic test for finding corroded connections or failing wires.
Okay. What about measuring amperage and resistance?
Amperage measurement tells you how much current is actually flowing. Useful for checking if a component is drawing too much current, like a shorted motor, or too little, like an open circuit. It's also key for finding parasitic drains, those sneaky key-off battery drains. Resistance measurement, usually done with the circuit off, checks continuity, making sure there's a complete path, and helps identify open circuits, infinite resistance, or shorts to ground, very low resistance where there shouldn't be.
So what are the main types of circuit problems technicians hunt for?
Broadly, you're looking for shorts, opens, or high resistance. A short circuit is an unintended path for current, often directly to ground, bypassing the load. This usually causes very high current flow and blows fuses. An open circuit is a break in the path no current can flow. A high resistance problem is like a bottleneck current flows, but it's restricted, causing voltage drops and preventing components from working properly.
And like other systems, we have diagnostic trouble codes here too.
Oh yes. Electrical and electronic systems generate plenty of DTCs. They often have specific prefixes: P for powertrain, B for body controllers like lighting, wipers, seats, C for chassis, ABS, steering, suspension, and U for network communication issues between modules.
U codes sound important with all the computers talking to each other.
Very important. Modern cars are networks on wheels. Scan tools are essential for reading these codes, looking at live data from sensors and modules, and using bidirectional controls to test actuators like window motors or door locks. We also need to understand basic components like relays, electromagnetic switches that let a low current circuit control a high current one, and diodes, which act like one-way valves for electricity. Hashtag tag B battery and starting system diagnosis and repair, 2.2%. Circling back to the battery, the starting point for all things electrical. A typical 12-volt car battery has 6 cells connected in series, each producing about 2.1 volts. Inside each cell are positive plates, lead oxide, and negative plates, lead, immersed in an electrolyte solution of sulfuric acid and water.
And there are different types.
Yes. You have traditional flooded batteries with removable caps to check electrolyte level, low maintenance types, which are mostly sealed but might have vents, and completely sealed maintenance-free types, including AGM, absorbent glass matte batteries, often used in vehicles with high electrical demands or start-stop systems.
How do you test them? We mentioned voltage and load testing.
Right. Open circuit voltage check first, 12.6 V or more means fully charged. Specific gravity check with the hydrometer for flooded batteries, 1.265 to 1.299 is typical. And the crucial load test, which measures its ability to deliver cold cranking amps, CCA. That tells you if it can handle the high current demand of the starter motor, especially when cold. Basic maintenance involves keeping the terminals clean and tight and checking the cables for corrosion or damage.
Okay. And the starting system itself, when it doesn't crank or cranks slowly.
The system is relatively simple. Battery, starter motor, which includes the solenoid, ignition switch, and the cables connecting them, possibly a starter relay. Diagnosis starts with the symptoms. Engine won't crank at all. Could be the battery, connections, ignition switch, neutral safety switch, relay, or solenoid.
Cranks slowly.
Usually battery, connections, high resistance in cables, voltage drop, or possibly a faulty starter motor drawing too much current. Cranks normally but won't start. That points away from the starting system itself and towards fuel, spark, or compression issues we discussed earlier.
How do you test the starter directly?
The starter current draw test measures the amperage it pulls during cranking, typically 200-400 amps, depending on the engine. Excessive draw suggests an internal starter problem or possibly a mechanically tight engine. Voltage drop tests on the battery positive cable to the starter and the ground cable are critical. You also check the voltage getting to the solenoid's trigger terminal when the key is turned to start. Common problems besides slow-no crank include noisy cranking, could be worn starter drive gear or damaged flywheel ring gear, or the starter drive not engaging the flywheel, solenoid issue or drive mechanism failure. It's a system every part needs to work. ###DOSI, Body Electrical Systems Diagnosis Diagnose and Repair, 5.7%.
Okay, let's move to the myriad of other electrical things in a car. Wipers, lights, gauges, windows. The body electrical systems. This seems like it could get complicated fast.
It definitely can. And that's why having access to good wiring diagrams and service information is absolutely non-negotiable here. Trying to trace circuits without a map is incredibly frustrating and inefficient.
So diagrams first. What about something like the wiper and washer system? Seems simple,
But they can have their own quirks. Diagnosis involves checking the wiper motor itself, the mechanical linkage that moves the arms, the multi-function switch that controls speed and washers, and the washer pump. Common issues are worn motor gears, broken linkage bushings, faulty switches, especially those complex column-mounted ones, or clogged washer nozzles.
Okay. The instrument cluster and driver information systems. The gauges, warning lights, displays. That's the driver's main interface with the car systems.
Exactly. Diagnosing issues here involves checking inputs from various sensors. For example, an inaccurate speedometer or tachometer reading could be caused by a faulty vehicle speed sensor, VSS signal, a problem in the wiring to the cluster, or an internal issue within the cluster itself. It often involves checking communication networks, like CAN bus, since the cluster gets information from multiple modules like the PCM or TCM.
And warning lights or malfunctioning gauges.
You need to diagnose the underlying system first. Is the oil pressure warning light on? Check the actual oil pressure and the pressure sensor switch circuit. Coolant temp gauge reading high. Verify the actual temperature and check the coolant temperature sensor circuit. Sometimes the fault is the sensor or wiring, sometimes it's the gauge or cluster, and sometimes it's indicating a real problem with the system being monitored.
Lighting systems. Headlights seem critical for safety. What's involved there?
Headlights come in different types: older sealed beams, replaceable composite bulbs, modern high-intensity discharge HID or LED units. Diagnosis involves checking bulbs, fuses, relays, switches, and wiring. Look for voltage drops caused by corroded connections, especially grounds, which are a common cause of dim lights. Headlight aiming is also critical for safety, ensuring the beam pattern illuminates the road correctly without blinding oncoming drivers. Specific aiming procedures are required.
And other lights. Brake lights, turn signals.
Similar principles. Check bulbs first, it's the most common failure. Then fuses, the switch, brake light switch, turn signal flasher switch, and wiring. Intermittent problems are often traced to bad grounds or loose connections. Using a test light or multimeter to trace voltage through the circuit is standard practice. ###D charging system diagnosis and repair, 1.2%. The charging system's job is to keep the battery charged and supply power to everything else once the engine is running. The heart of it is the alternator,
Which generates AC current.
Yes, the alternator generates AC voltage internally. Inside, there's a rectifier bridge, a set of diodes that converts that AC into the DC voltage the car's electrical system uses. There's also a voltage regulator, usually built into the alternator now, whose job is to control the alternator's output voltage.
Keep it in the right range.
Exactly. It monitors the battery voltage and adjusts the alternator's field current to keep the system voltage stable, typically between about 13.5 and 14.5 volts when the engine is running. Too low and the battery won't charge. Too high and you can damage the battery and other electronics.
What are the main internal parts?
You've got the stator, the stationary windings where voltage is induced, the rotor, a spinning electromagnet driven by the engine belt, brushes and slip rings to get current to the spinning rotor, the rectifier, and the voltage regulator.
So how do you diagnose charging system problems, like if the battery keeps dying or the charge light comes on?
First, check the drive belt. Is it loose, worn, slipping? The alternator can't work if it's not being spun properly. Then check the charging voltage at the battery terminals with the engine running. It should be in that 13.5, 14.5 V range. If it's low, like battery voltage, 12.6 V or less, the alternator isn't charging. If it's too high, the regulator might be faulty. You can also do a charging current output test using an ammeter or specialized tester to see if the alternator can produce its rated amperage under load. Connecting this back, the charging system is vital. It keeps the battery ready for the starting system and powers everything else. A failure here quickly leads to a dead battery and a car that won't go anywhere.
Okay, let's move on to do arguably the most critical safety system.
Yeah.
Brakes. Getting the car to stop reliably is, well, pretty important.
Understatement of the year. And brakes have evolved significantly, from simple hydraulics to incredibly sophisticated electronic systems like ABS and stability control. But understanding the core hydraulic principles is still the foundation for everything. ##A, hydraulic system diagnosis and repair, 2.4%. The master cylinder is command central for the hydraulic system. Nearly all modern cars use a tandem master cylinder, meaning it has two separate pistons and circuits inside, usually one for front brakes and one for rear.
For safety, right, if one circuit fails.
Exactly. If one circuit develops a leak, you still have braking on the other two wheels. Inside, you have the primary and secondary pistons with seals and return springs. When you push the pedal, the pistons move, pushing fluid into the brake lines. Compensating and bypass ports are small holes connecting the cylinder bore to the reservoir. They allow fluid to return when the pedal is released and compensate for fluid expansion or pad wear.
What about residual pressure check valves?
Those are typically used only in the circuit going to drum brakes. They maintain a very slight pressure, a few psi, in the lines when the pedal is released. This keeps the drum brake shoe springs slightly preloaded, ensuring quicker engagement and helping prevent air from being drawn past the wheel cylinder seals. Diagnosing master cylinder issues often involves symptoms like a spongy pedal, air in the system, a pedal that slowly sinks to the floor under steady pressure, internal leak past a piston seal, or fluid level issues in the reservoir. That dual circuit design is a fundamental safety feature you rely on every time you brake.
And the fluid itself. DOT3, DOT4, what's important there?
Brake fluid is hygroscopic, meaning it absorbs moisture from the air over time. This moisture lowers the fluid's boiling point. If the fluid boils under heavy braking, creating steam pockets, you lose hydraulic pressure, that's brake fade, and it's dangerous. That's why regular fluid flushes are recommended. DOT3 and DOT4 have different minimum boiling points. DOT4 is higher. They are generally compatible, but you should always use the type specified by the manufacturer. DOT5 is silicone-based and not compatible with DOT34 systems.
Okay. Lines and hoses.
Steel brake lines need inspection for rust, kinks, or damage. Flexible rubber hoses at the wheels need checking for cracks, bulges, chafing, or leaks. Repairs to lines require proper double flaring techniques to ensure a leak-proof seal. Hoses should be replaced if they show any signs of deterioration.
What about proportioning valves and pressure differential valves?
A proportioning valve is used to limit the pressure increase to the rear brakes, especially during hard stops. This helps prevent rear wheel lockup, which can cause instability. The pressure differential valve, often part of a combination valve, monitors pressure in the two separate hydraulic circuits. If one circuit loses pressure, like from a leak, the valve shifts, closing off the leaking circuit and often activating a warning light on the dash.
And bleeding brakes.
Yeah.
Getting the air out.
Absolutely essential anytime the hydraulic system is opened. Air compresses, fluid doesn't. Air bubbles make the pedal feel spongy and reduce braking effectiveness. Procedures vary: manual bleeding, pump and hold, vacuum bleeding, pressure bleeding, but the goal is the same. Push fresh fluid through the lines until all air is expelled from the bleed screws at each wheel cylinder or caliper. #B. Disc brake diagnosis and repair, 2.7%. Disc brakes are the standard now, especially on front wheels. You have the caliper, which houses the pistons and brake pads. Calipers can be fixed, bolted rigidly, pistons on both sides, or, more commonly, floating, slides on pins, piston usually on one side. The rotor is the disc that spins with the wheel, and the pads are the friction material squeezed against the rotor by the caliper. Anti-rattle springs or clips are often used to keep the pads from vibrating and making noise.
What are common symptoms of disc brake problems?
Noise is a big one. Squealing often indicates worn pads. Many have wear indicators that squeal. Glazed pads or improper hardware installation. Groaning or grinding usually means metal-on-metal contact pads worn down to the backing plate, severely damaging the rotor. Chattering can indicate rotor issues or loose components.
What about pulsation in the pedal?
Brake pedal pulsation during braking is almost always caused by variations in the rotor's thickness, parallelism variation, or by lateral runout, warping. As the uneven rotor spins between the pads, it pushes the caliper piston back and forth slightly, creating that pulsating feeling back through the fluid to the pedal. A pull to one side during braking usually means one brake is working harder than the other, maybe a stuck caliper on the non-pulling side, or contaminated pads on the pulling side.
So inspection involves
Checking pad thickness is obvious. Inspecting the rotor surface for deep scoring, cracks, or signs of overheating, blue or black discoloration. Measuring the rotor is critical. Use a micrometer to check its thickness against the minimum specifications stamped on the rotor hub. Use a dial indicator to measure lateral runout. Excessive runout or thickness below minimum means the rotor needs replacement, or possibly machining if it's still thick enough and runout isn't too severe. You also need to check that floating calipers slide freely on their pins.
and repairs.
Pad replacement is common, rotor replacement or machining. Sometimes caliper service is needed: cleaning, lubricating slide pins, possibly rebuilding or replacing the caliper if a piston is sticking or leaking. Proper cleaning and lubrication of mounting points and hardware is key to preventing noise and ensuring even pad wear. That slight distortion and return of the caliper piston we mentioned is vital for preventing drag. ###C. Electronic brake control systems, ABS, TCS, ESC diagnosis and repair, 2.4%. Now we get into the electronic safety nets. ABS, anti-lock braking system, is the foundation. Its job is to prevent wheels from locking up during hard braking.
Why is that important?
A locked skidding wheel has much less traction than a rolling wheel, both for stopping and steering. ABS rapidly pulses the brake pressure to individual wheels, keeping them rotating just below the point of lockup. This allows the driver to maintain steering control while braking hard, which can be crucial for avoiding obstacles.
Okay. And TCS, traction control.
KCS works kind of like ABS in reverse. It prevents wheel spin during acceleration, especially on slippery surfaces. If a drive wheel starts spinning faster than the non-drive wheels, TCS can apply the brake to that spinning wheel and/or reduce engine power to help regain traction.
And ESC, stability control.
Electronic stability control is even more sophisticated. It uses sensors to detect if the vehicle is starting to skid or spin out of control during a turn or evasive maneuver, like swerving. It can then intervene by applying individual brakes selectively, maybe braking the outside front wheel to counteract oversteer, rear skid, or the inside rear wheel to counteract understeer, front skid, and also modulate engine power to help bring the vehicle back under control.
Wow. What are the core components making all this happen?
You have wheel speed sensors, WSS, at each wheel, constantly monitoring rotation speed. There's an electronic control unit, ECU, the brain, processing sensor data, WSS, steering angle sensor, yaw rate sensor, etc., and a hydraulic control unit, HCU, or modulator, which contains solenoid valves and a pump that can rapidly modulate brake pressure to individual wheels independently of the driver's pedal input.
Diagnosis relies heavily on the electronics then.
Absolutely. It starts with checking for DTCs using a scan tool. Scan tool data is crucial. You can monitor individual wheel speed sensor readings in real time to look for dropouts or erratic signals. Testing the sensors themselves might involve checking resistance or using a scope to look at their AC voltage output for magnetic types. These systems are designed to maintain control before the driver loses it, a huge leap in active safety. ###D. Drum brake diagnosis and repair, 1.5%. Drum brakes, while fading on passenger cars, are still around, especially on rear axles or as parking brakes. Inside the drum, you have brake shoes that push outwards against the rotating drum surface. Wheel cylinders use hydraulic pressure to push the shoes out. Springs pull the shoes back when pressure is released. Adjusters maintain the correct shoe-to-drum clearance as the shoes wear, and the backing plate holds everything together.
Are there different designs?
Yes. Common designs include duo servo, where the action of the primary leading shoe helps apply the secondary trailing shoe, creating a self-energizing effect for more stopping power. Leading trailing designs are simpler without the servo action. Diagnosis involves listening for noise, scraping, grinding, checking for pulling, or addressing pedal feel issues. Inspection means pulling the drums off to check shoe lining thickness, look for contamination like gear oil from a leaking axle seal, inspect the drum surface for scoring or heat checks, and check the wheel cylinders for leaks.
In repairs.
Replacing worn shoes and drums is common. Servicing or replacing leaky wheel cylinders. Replacing the hardware kit, all the springs, clips, and adjusters is highly recommended whenever doing shoe replacement, as springs lose tension over time. And proper adjustment of the shoe-to-drum clearance is critical for good pedal feel and braking performance. There's a maximum diameter specification for drums. If they wear beyond that, they must be replaced. Hashtag tag e-parking brakes, 1.5%. The parking brake or emergency brake is usually a purely mechanical system. It uses cables, levers, and sometimes linkages to physically apply the rear brakes, either the drum brake, shoes, or sometimes a separate small mechanical caliper on disc brake systems.
What goes wrong with them?
Common issues are the brake not holding the vehicle securely, often due to stretched cables or improper adjustment, or the brake dragging after release, usually because of seized cables or sticky mechanisms at the wheels. Excessive travel in the pedal or lever typically indicates a need for adjustment. Hashtag tag power assist units diagnosis and repair, 1.5%. Making it easier to push that brake pedal are the power assist units. The most common is the vacuum booster, which uses engine vacuum acting on a large diaphragm to multiply the force you apply to the pedal.
So if the engine stalls, you lose power assist.
Yes, or it becomes significantly reduced after 1 or 2 applications using stored vacuum. The other type is Hydro Boost, which uses hydraulic pressure generated by the power steering pump to provide brake assist. These are often found on diesel trucks or vehicles with limited engine vacuum.
How do you diagnose problems?
The main symptom of failure is a hard pedal. It requires much more physical effort to stop the car. You might also hear hissing sounds from a leaking vacuum booster diaphragm. Diagnosis involves checking vacuum supply to the booster or checking power steering system pressure and operation for Hydro Boost units. These units are critical. Loss of assist can feel like total brake failure to the driver, even though the base hydraulic brakes still work if you push hard enough. Hashtag tag G wheel bearings, 1.2%. Wheel bearings let the wheels spin freely while supporting the vehicle's weight. Older designs often use tapered roller bearings that require periodic lubrication and adjustment. Most modern cars use sealed hub and bearing assemblies that are non-serviceable and replaced as a unit.
What are the signs of a failing wheel bearing?
Noise is the most common symptom, a humming, rumbling, or growling sound that typically changes pitch or intensity with vehicle speed or when turning. You might also detect excessive looseness or play when rocking the wheel top to bottom or side to side.
How is service performed?
For older tapered bearings, service involves removing the bearing races, cleaning, inspecting, repacking with grease, reinstalling, and carefully adjusting the bearing preload and play. For modern sealed hub assemblies, service means replacement. This often requires specialized pullers or presses to remove the old hub and install the new one correctly without damaging the bearing. Checking end play on adjustable bearings is often done with a dial indicator to ensure it's within the specified very small range. Hashtag tag H-brakes, 4.6%.
Okay, pulling this whole brake section together, what's the big picture takeaway, the fundamental message for anyone working on brakes?
It's really about appreciating the system's integrity. Every single part, from the pedal linkage to the master cylinder, the fluid, the lines, the calipers or wheel cylinders, the pads or shoes, the rotors or drums, the electronic controls like ABS, even the wheel bearings supporting it all. Everything has to work correctly and work together. It demands a holistic approach. You can't just focus on one part in isolation. A failure anywhere compromises safety. It's about ensuring that from the moment the driver touches the pedal to the moment the vehicle stops, everything functions precisely as designed. The system is only as good as its weakest link.
All right, let's move on to the systems that literally keep the car connected to the road and going where you point it. Suspension and steering. These are all about ride comfort, handling precision, and ultimately control.
Absolutely. These systems have a huge impact on how the car feels to drive, how stable it is, and how safely it responds, especially in emergency situations or on rough roads. It's all about maintaining that tire contact patch and allowing the driver precise control. Hashtag tag A. Suspension systems diagnosis and repair, 6.1%. There are several common suspension designs. You've got the classic short long arm or SLA double wishbone setup. Very common is the McPherson strut, which combines the spring and shock absorber into one unit that also serves as the upper pivot point. Then you have simpler coil spring or leaf spring designs, often used on rear axles.
What are the key components we're looking at?
Control arms or wishbones locate the wheel assembly. Ball joints allow the steering knuckle to pivot for steering and move up and down with suspension travel. Springs, coil, leaf, or torsion bar support the vehicle's weight. Shock absorbers or struts dampen the spring oscillations, controlling ride and handling. And the stabilizer bar, or anti-roll bar, connects the left and right sides to reduce body lean during cornering.
How do you start diagnosing suspension problems? Rattles, clunks, poor rides?
It usually starts with a road test. Drive over different surfaces, listen for noises. Clunks over bumps might be worn bushings or ball joints. Squeaks could be dry bushings. Feel how the car handles. Does it wander? Does it feel unstable? Then, a thorough visual inspection on a lift is crucial. Look closely at all the rubber bushings in the control arms and stabilizer bar links. Are they cracked, torn, deformed, or oil-soaked? Check the ball joints for torn boots or excessive play. Look for leaking shock absorbers or struts. Oily residue is a dead giveaway. Inspect springs for breaks. Check stabilizer bar links for damage or looseness. Sometimes just seeing a badly cracked control arm bushing tells you exactly where that clunk is coming from.
And repairs often involve replacing these worn parts.
Yes. Control arm bushing replacement can be involved, often requiring hydraulic presses or special tools to remove the old bushing and install the new one without damaging the arm. Ball joint replacement is common. Tie rod end replacement too, though that's technically steering linkage. Replacing strut cartridges or entire strut assemblies is also frequent maintenance. Now, you mentioned the stabilizer bar. It raises an interesting question. Why is it so important for handling if it doesn't support weight?
Yeah, how does it work?
It acts like a torsion spring connecting the left and right suspension components. When one wheel hits a bump, the bar twists slightly but allows independent movement. But when the car corners and the body tries to lean or roll, both sides of the suspension move relative to the body. The stabilizer bar resists this twisting motion, effectively transferring some of the suspension load from the heavily loaded outer wheel to the inner wheel. This keeps the car flatter, reduces body roll, and improves tire grip and stability during cornering. #B steering systems diagnosis and repair, 2.9%. Moving to steering. For power steering systems, checking the fluid is step 1. What type is required? Often it's specific power steering fluid, but sometimes it's automatic transmission fluid, ATF. Check the level and condition. Is it dark, burnt smelling, or contaminated?
What about the power steering pump itself?
Pumps can get noisy. Whining is a common complaint, often worse when turning. Leaks are also frequent. You can perform a power steering pressure test using a specialized gauge to measure the maximum pressure the pump can produce. Low pressure indicates a weak pump. Normal pressure but still lack of assist might point to the steering gear itself. Simpler repairs involve adjusting or replacing the drive belt or replacing the pump pulley.
And the steering gear, the part that actually turns the wheels.
Two main types here. Rack and pinion is most common now. The steering wheel turns a pinion gear, which moves a toothed rack left or right, directly connected to the tie rods. Older systems use a recirculating ball steering gear, worm and sector, which is more complex and usually found on trucks or older cars. Diagnosis involves checking for play or looseness in the gear, looking for leaks from seals, and checking the gear's preload adjustment if applicable.
And the linkage connecting the gear to the wheels.
On a rack and pinion system, you have inner and outer tie rod ends. On steering gear systems, you typically have a pitman arm connected to the gear, an idler arm supporting the other end of a center link or drag link, and then inner and outer tie rod ends connecting the center link to the steering knuckles. All these pivot points, tie rod ends, ball joints, idler arm pivots, wear out over time. Diagnosis involves checking each joint for excessive play or looseness. Worn linkage causes vague steering feel, wandering, and uneven tire wear. A pressure test, as mentioned, is great for differentiating pump issues from gear issues. #C, wheel alignment diagnosis, adjustment, and repair, 2.7%. Wheel alignment is critical. It ensures the wheels are pointing in the right direction relative to each other and the vehicle centerline. The main angles are camber, caster, and toe.
Can you quickly define those?
Sure. Camber is the inward or outward tilt of the top of the tire when viewed from the front. Too much negative camber, top tilted in, where's the inside edge of the tire. Too much positive, top tilted out, where's the outside edge. Caster is the forward or rearward tilt of the steering axis when viewed from the side. Positive caster helps with steering stability and returnability, the wheel wanting to return to straight ahead. Toe is the angle of the wheels relative to each other when viewed from above. Toe in means the front edges are closer together than the rear edges. Toe out is the opposite. Incorrect toe is a major cause of rapid tire wear, often causing feathering across the tread.
How do you diagnose alignment problems, besides just seeing weird tire wear?
Uneven tire wear is the biggest clue. Feathering, cupping, one-sided wear. These patterns point directly to specific alignment issues. Other symptoms include the steering wheel being off-center when driving straight or the vehicle pulling consistently to one side. Diagnosis is done using sophisticated alignment machines that use lasers or cameras to measure all the angles precisely. Adjustment procedures then involve turning threaded adjusters, rotating eccentric cams, or sometimes adding shims to bring camber, caster, and toe back within the manufacturer's specified range. Hashtag tag tag D wheel and tire diagnosis and service 1.2%. And that brings us to the wheels and tires themselves. Regular inspection is vital. Check tire pressure. It's critical for safety, handling, tire life, and fuel economy. Look for abnormal wear patterns. As we just discussed, they're symptoms of other problems. Check for cuts, bulges, or other damage.
Basic services.
Tire rotation is key to promoting even wear, especially on vehicles where front and rear tires wear differently. Balancing the wheel and tire assembly is crucial for preventing vibrations, particularly at highway speeds. An out-of-balance tire can cause annoying shakes and also accelerate wear on suspension and steering components. It's interesting, though, how often the first thing a driver notices is that uneven tire wear. It acts like an early warning sign that prompts investigation into the underlying alignment or suspension problem. The tires tell a story.
Last but not least, let's touch on the system that keeps us comfortable inside.
Yeah.
HVAC. Heating, ventilation, and air conditioning. More than just comfort, it's important for visibility too, right?
Absolutely. Defrosting windshields and defogging windows are critical safety functions provided by the HVAC system. And yes, the AC side especially is a fascinating thermodynamic cycle, a constant interplay of pressure and temperature changes to move heat from inside the cabin to the outside air. Hashtag AC system service, diagnosis, and repair, 1.2%. When talking AC, we have to mention the refrigerant, the fluid that actually does the cooling. R134A has been the standard for years, but now we're seeing the widespread adoption of R1234i, which has a much lower global warming potential. Handling these refrigerants requires specific equipment and certification due to environmental regulations and, with R1234, flammability concerns.
What are the main components in the AC loop?
You've got the compressor, which is the heart of the system, pumping the refrigerant. The condenser, usually in front of the radiator, where hot, high-pressure refrigerant gas releases heat and condenses into a high-pressure liquid. The evaporator, typically inside the dashboard, where cold, low-pressure liquid refrigerant absorbs heat from the cabin air and boils back into a gas. This is where the cooling happens. And then components like the accumulator dryer stores refrigerant and removes moisture, or receiver dryer, similar function, and an expansion valve or orifice tube creates a pressure drop, allowing the refrigerant to get very cold before the evaporator.
So it's a continuous cycle.
Exactly. Compression, hot gas, condensation, warm liquid, expansion, cold liquid gas mix, evaporation, cold gas absorbing heat. That cycle repeats constantly when the AC is on.
How do you diagnose AC problems, like no cold air?
Diagnosis usually starts with checking system pressures, using a manifold gauge set connected to the high and low side service ports. Comparing these pressures to ambient temperature charts helps determine if the refrigerant charge is correct, if there's a restriction, or if the compressor is weak. Leak detection is also very common, using UV dye added to the system or electronic refrigerant sniffers. Performance issues like insufficient cooling can be caused by low refrigerant, poor airflow over the condenser or evaporator, or internal system problems. Looking at a diagram, say for a cycling clutch orifice tube system, helps visualize that refrigerant flow and where problems might occur. Now, this brings up a critical point. Why is measuring the exact amount of refrigerant so important when recharging a system?
Yeah, you can't just top it off like engine oil, can you?
Definitely not. AC systems are critically charged, too little refrigerant, undercharged, and cooling performance suffers dramatically because there isn't enough fluid circulating to absorb heat effectively. Too much refrigerant, overcharged, and pressures can get dangerously high, potentially damaging the compressor, reducing cooling efficiency because the refrigerant can't properly change state, and causing the system to cycle improperly or shut down. You must evacuate the system completely and recharge with the precise weight of refrigerant specified by the manufacturer for optimal performance and longevity. Precision is everything in AC work. Hashtag tag outro.
Wow. Okay, we have covered an incredible amount of technical ground today. A real deep dive from the hydraulics of a torque converter through engine sensors, electrical pathways, brake systems, suspension geometry, right up to AC refrigerants. It's a journey through the core systems that make a vehicle function.
It really is. And if you connect all these pieces, the big picture that emerges is just how interconnected everything is. You know, an electrical problem in a sensor can cause a transmission to shift poorly. A suspension issue can lead to premature tire wear. A cooling system fault can destroy an engine. They aren't isolated systems.
So critical thinking is key, not just knowing the facts, but seeing the relationships.
Exactly. It's about connecting the dots, understanding the why behind the symptom you're seeing or the code you're reading. It's about building that comprehensive mental model of the entire vehicle as one integrated machine.
So, what does this all mean for you listening in? Whether you're wrenching on cars every day, studying for your ASEs, or just fascinated by how they work, next time you're in a vehicle, or maybe troubleshooting an issue, think beyond just the immediate symptom. Consider that whole intricate web of systems we've explored. And here's something to mull over, your provocative thought for this deep dive. What single system, in your view, has the most surprising or maybe unexpected impact on the entire vehicle's operation or feel when it malfunctions, and why do you think that is? Something to chew on until our next deep dive.